So here's the question. So you have a charge, a Q, a Q, a Q, and a Q. And they're all equal to each other. So this is 1, I think I call this one 2, this is 3, and this is 4. Is that how I labeled them in the class? Okay, this is 2, okay. All right, and so these things are on a square. Like so. And what is the length of the square? The edge of the square is 1 centimeter. So let me call this the length, and this is 1 centimeter. Now for calculation purposes, always make sure you convert into the proper unit. So our official unit for a distance is a meter, so not a centimeter. So this is 0.01 meters. And each charge, they're all equal. This is 10 to the minus 9 coulombs. So 1 times 10 to the minus 9 coulombs. So this is a nano coulomb basically. So that's how much that is. And then the question is, what is the electric field for part B? What is the electric field over here? This is the question, okay? So in the middle of one of the edges of the square, what is the electric field? So what's happening is all of these things are sending electric fields. So each of these charges are like fans blowing air. They're throwing out electric field. So this throws out an electric field this way. This throws an electric field this way. These two will cancel each other out. Okay, the vectors, they're basically head to head, they're equal in magnitude. So E 2 and E4, these two are going to cancel. Now that leaves these two electric fields, this one over here and this one over here. So these will not cancel. So they need to be added up vectorially. So now to find the magnitude of the electric fields, so E1 is equal to E3, and that's equal to a K, a Q over R squared. And this is R, by the way. This is R. Okay, any questions so far? Okay, so the electric field points away from a positive charge and it's hitting over here. The value of that is K, Q, or R squared. So these are magnitudes. So this is a magnitude equation. It has no information about the direction. There are no signs, no plus, minus. That's how strong the electric field is magnitude-wise. And that's given by Coulomb's law with just the one charge. Is this clear? Okay. So now you have to add these up. We need to find R. So if you look at R, this is R, this is half L, and this is L. Now this indeed is a right angle triangle. So over here, for something like this, feel free to use Pythagorean theorem. So here you have R squared. The hypotenuse squared is the opposite squared over the adjacent squared. Okay, is this clear so far? Okay, and so R. So in fact, the formula requires R squared. Let's just leave it as R squared. Why do a square root? Yeah, you want an R squared to put into that. So this is now equal to, let's find it. the L was what did I say? The L was 1 centimeter. So it's 0.01, okay, over 2 squared plus 0.01 squared. So, so I just put in the numbers for these over here. And so this is equal to, let me bring up my calculator here. So you have 0.01 Oh, Maya, you have a question?
Yes, I was wondering why the triangle isn't considered an equilateral triangle because it's within a square. Like, wouldn't all the sides be the same length and all the angles be the same?
Correct, but this is not the whole square. It's a slice of the pie. Does that make sense? For the square, yes, these are equal, but this is not the whole square. So it's one of those square pizzas, I think, which is the brand that does that? Little Caesars, I think, but it's a square pizza. It's not a circular one. You threw out like 2/3 of that pizza. This is just one slice. So this slice is no longer symmetric. The way it was cut.
Okay.
Okay. So this is a awkwardly cut slice from the pizza.
Okay.
So sure. So this part is the same as the others, but here you went halfway. So as a result, this is not equal to that, and this ends up being a diagonal. So this is a little triangular slice, and these are all of the three things are different over here, all the three sides. Okay, and so this is equal to what is it equal to? 1.25 10 to the minus 4 meter squared. Okay. And by the way, you can chime in at any time. You don't even have to raise your hand. If you have a question, just turn your mic on and speak away. Okay, so this is 1 point. So this is r squared. So now let me call this r squared. I will call this equation 2. And this over here, this is my equation 1. So I can now put equation 2 into equation 1, and I can solve for the electric field. So put these in there. So now you have E1. So put okay, so put equation 2 into equation 1, and then that tells you that E1 is equal to E3 is equal to K. So K is 9 times 10 to the 9, and Q was, what was Q? It's a nanocoulomb, 10 to the minus 9. So you have 1 times 10 to the minus 9 coulombs. And r squared, that's where you put in this stuff here, 1.25 10 to the minus 4. Okay, is this clear so far? So we did this is the electric field. This is comes from Coulomb's law. If you just take one of the charges, that's the electric field part, KQ over r squared. The r was not given straightforwardly. So there we had to find r from the triangle, and there is this r over here. And then we just put that r squared into this equation 1, and this is the electric field. So let me go ahead and crunch that out. So this is equal to 9 And I'm kind of punching his numbers into the calculator in a hurry. So any of you can, feel free to like just recheck this calculation, make sure the numbers are correct. Okay, so I seem to be getting 7.2 10 to the 4. Okay, is this clear? Okay, so that's the magnitude of the electric field. So we need to we started by saying that the electric field, this E1 and E2 and E4, they cancel each other out because they are head on. These two don't cancel, so we need to add them. You cannot just add these numbers because these are the magnitude. You have to add them as vectors. So these two are vectors. So this is just the magnitude. Now we need to find the x components and the y components. So next, add E1 and E2 vectorially. Okay. So those are, so you can't just add these as numbers because they have direction. They're not going in the same direction. Then you could add them as numbers, but they have different directions, so it's a little bit more awkward. So to do that, you have to add the components. So let me go to the next sheet of paper here. Let's see. See, unlike a whiteboard in class, this never gets erased. It's always there. So you can like refer back to what we discussed 2 minutes ago. I still have that sheet of paper. Okay, so to add these things vectorially, this means that the E total, which is the sum of E1 plus E2, the x component of that, E total x, is equal to E1x. Oh, this is not 2, this is 3 actually. 3, okay. 3. The one below it, it was E3. So this is E1x plus E3x. So this is the rule for adding vector. The x component of the total is the x component of the first one plus the x component of the second one. You add them up. That's the x of the total. So you have to do it component by component. Do it for x, do it for y, then put everything together. Okay, so now here, so this is equal to the magnitude of E1 times cosine of its angle. So this is equal to 7.2 10 to the 4 times cosine of theta for E1. And then plus 7.2 10 to the 4 cosine of theta for E3. Okay, any questions so far? Just look at this, think about it, make sure nothing is missing. If you make sure you never missed a single step, you'll kind of learn faster and everything will be more efficient. So just look at this for a second. Okay, everybody's fine?
So when you're
Yeah.
adding vectorially, do you always have to add the x and the y component? You would never just do like just the x component or just the y component?
Sometimes one of the components could be 0. So, I mean, all of the y or all of the x components could be 0. In that case, you can skip that part. So like going back to this, we kind of used this graphical way of adding the vectors and came to the conclusion quickly that these are 0. But if you were to do this in this way with x and y component, they are vertically up and down. So they have no x component. X is horizontal. They're completely up and down. So you would do it just for the y. You could do it for the x. There's no harm. The equations will handle that for you automatically. So in theory, you never have to make any decision. If you use this process with the component, just do both components to be safe. Not taking shortcuts is safer. Shortcuts don't save you much time, but there's a risk of neglecting something that needed to be considered, basically. Okay, so yeah, this is the safest way of doing it. Do it for the x, do it for the y, and then go from there. And so this is so now the big question is what are these angles here? So let's label this equation. So this is equation 3. So we need to find these angles. So let's go back to the diagram now. So I'll just redraw that whole thing over here. So here is Q1 and this was a Q3, and they sit on the square like so. This is shooting out an electric field this way. This is E3. This is shooting an electric field this way. That's E1. Those are the two electric fields. Now draw the axes. So here are the axes. And here's my y. You see how everything proceeds in a sort of methodical and a systematic manner. You avoid making mistake. So the angle, the official angle of a vector, you need to put the tail at the origin where the x and the y meet. And the official E1, put the tail at the origin over here. And then the angle is somebody is waiting to be admitted. Here we go. Okay, Sai, were you able to get in? Okay. So the official angle is this one over here. So this is a theta for electric field E3. Right? You start from the x-axis, you go counterclockwise, never clockwise, and you end up where the vector is pointing. That's E3 over here. And for this vector here, use a different color. For E1, again, you start from the x-axis, counterclockwise, keep going until you come over here. So this is theta for E1. Okay, any questions about how you find the angles? Okay, so now we need to find this angle. So what are these angles? So look at this thing over here. This angle, it's the same as this angle. It's kind of a reflection of that angle over here. Okay, so these are corresponding angles. This is a parallel line. This is a parallel line. If you cut two parallel lines by a third parallel line like this, okay, then this angle here is the same as this angle over here. When you cut two parallel lines with a straight line, this angle and this angle, they're equal. They're called corresponding angles, I think. So those angles are equal. So if we find this, we found that angle. As far as this angle over here is concerned, so let's do the E3 theta for E3 first. Okay. So here in this triangle, this is L, this is L, this is L over 2, right? And so the opposite over the adjacent, that's the tangent of the angle. So here, the tangent of this angle theta 3, and this is equal to opposite over adjacent, and that is equal to L over 2 over L, and that's equal to 1/2. You see how we are proceeding to find the angle? So anytime you reach a dead end, put a label on that equation, like equation 3, and like set it aside, and then go find that angle and come back and put it into equation 3. So theta 3 is the arctangent of 1/2. So theta 3 is equal to a tan inverse of 1/2. And that is equal to, let's see. Oh, okay. That seems to be 26.6 degrees. Okay, so I just plugged it into my little calculator app here, and that's what it gave me. Any questions? Okay, so that's this is it's not a cube. This is a theta. It's an angle. That's that angle. Okay, and now this is Q3. Now we have this is theta 3. Now we have to find the theta for the other one, which is the other one over here. That's E1 over here. So I've been calling these theta of, just looking at what I have before, this is E3. E3. So theta of the electric field vector coming from charge number 3. So that's that theta. Make sure all of this is completely clear. Let me know if any part of this is suspicious. Okay, so on to the next one over here. So now we need to find this angle over here. Notice that these two angles, they're equal. These two angles are equal from the symmetry. They're exactly equal. So this theta for E1, this yellow thing over here, or orange thing, depending on your color scheme of your monitor, this is, if you went all the way around and came here, that would be 360 degrees. So it's 360 degrees, and you back off by that angle, 26.6 degrees. So theta 1 is, if you went all the way around and came over here, that would be 360. Then you reverse and come back here. So you have to reverse by how much? By 26 degrees, these two angles. So theta for E1, this is equal to 360 minus 26.6. And this appears to be 333.4. There it is. So it's slightly less than 360 because you have to back off a little bit. And now put these. So this is equations, this is equation 4 and this is equation 5. Go back and put these equations into equation 3. That's where you needed to know those angles. So put these, put 4 and 5 into equation 3, which is this equation floating up here. So when you do that, you have 7.2 10 to the 4 and cosine. Go ahead and put this angle in there and do the same for the other one. So so you have, and we were calculating E total X. So this will be 7.2 10 to the 4 times cosine of, what was it, 333.4. 333. 333.4. Okay, and then plus 7.2 10 to the 4 cosine of 26.6. There we go. So we now have, so now we can crunch it out. So let's crunch. So we have So the 89.4, 0.894. So if you have a calculator handy, just go ahead and recheck all of my calculations. Make sure I didn't punch the wrong numbers in the calculator. So this appears to be 0.894. So let me just recheck here. Well, okay. So 0.894. And cosine of 26.6 is also 0.8942. And so this whole thing is equal to 7.2 1.29 10 to the 5. And this is the electric field, so the unit is newtons per coulomb. Okay, is this clear? Any questions? Does this agree with the answer in the book? It does? Okay, good. Okay, so the story had a happy ending there. Okay, and so this is the x component. Now how about the y component? Okay. So the y component, intuitively or graphically, you can figure out that it's going to vanish, but as a matter of practice, let's just go ahead and do that. So E total y, and that's equal to the same equation you had. It's the magnitude times sine of theta. So it's 7.2 10 to the 4, a sine of a theta E1 plus 7.2 10 to the 4 sine of theta E3. Okay, so this just to compare. So it's the same for the x. It's the same equation as you had for the x. You just replace the cosine theta with sine theta. That immediately gives you the y component of the same thing. So this is the total y. That's the total x. So now when you crunch this, when you crunch this, put in the values of theta. Theta 1 was 3. What was it? 333.4. This was 26.6. And and when you crunch this out, you'll find this is equal to 0. Because these two signs, they have the opposite, they're equal and opposite. So this will equal 0. So now you have the vector. So the electric field, the whole question, this has a x and y component. And those are equal to, the x was 1.295 10 to the 5 and 0. So those are the x component. The x, that's the x and the y component. And the angle, this is equal to the angle of a vector. The angle of a vector, anytime this drops below out of view, just let me know. So the angle of a vector is the arc tangent of the y over the x. So y over x, so this is equal to 0 over 1.295 10 to the 5. And that's equal to 0. So there's your vector. So the final vector, E total, it basically looks like this. and the magnitude is 1.295 10 to the 5 newtons per coulomb. And that's how this business works. Okay, is this clear? Any questions? Okay. And then, okay. So there's this question. Let's do the last one, 16.57, because it's simple and can be done in a couple of minutes. Okay, so here, this is that question now. Okay, 16.57. You have a dipole plus minus q and surrounded by a Gaussian surface. So the first part only, what's the electric flux through that surface? So let's do that one. Ooh, I moved the wrong thing. My goodness. So you have a dipole, it has a plus q and minus q, and they're separated by a distance a. The dipole moment, as you may recall, the P is equal to q times d. So in this case, it's q times a. But as far as the flux is concerned, here's a closed surface around this thing over here. So this plus q is sending flux outward. Remember the electric field lines? They point out like this. And the minus q, the negative charge is like a vacuum cleaner. The electric field lines are pointing inward. So the total lines end up, the number of lines which are leaving versus lines which are entering, they end up, they cancel each other out. The total flux is going to be 0. This can also be shown with Gauss's law. So from Gauss's law, you have the phi enclosed. This is equal to 4 pi kq inside enclosed. And this is equal to 0, because this is equal to plus q minus q. There is no net charge enclosed. So as a result, these two things will basically cancel each other out. As many lines are leaving as are being sucked in by the negative charge over here. So the total flux is equal to 0. And this is a quick application of Gauss's law and the concept of flux and electric field lines entering and exiting. Okay, any questions, any thoughts about this? Okay, so let's see. That leaves 16.45, which is also equally straightforward. That's an application of the equation for flux. So this is the last one. And you have a plane with a surface area 0.01 on edge. So here, this is once again a square like we had before. All sides are equal over here. And this L is equal to 0.1 meters in this case. It's placed in a region of uniform electric field of magnitude so much. So you have an electric field blowing this way. This E, the value of this E is equal to 24.6 newtons per coulomb. And then the angle between the surface is normal and the electric field is 33 degrees. So here, so this is kind of at an angle over here. This is 33 degrees. Okay. So this is the setup that you have. You have a surface has a normal. So when you move the surface around, this is like the axis of the area. And then the electric field, it was flowing like this. So there's an angle of 33 degrees between these two. So the amount of lines that you catch, the amount of flux, that's equal to how strong the electric field is. A stronger field means more lines going this way. The bigger the area, the bigger the fishing net, the more you catch. And you want that angle to be 0 degrees. So the surface is facing that. It's not 0 degrees. So you're going to miss out on some of the fun over here. But this flux, this is equal to E dot A, which is EA cosine of theta. Okay, and so this is a dot is an abbreviation for the cosine theta. And so this is equal to 24.6 times the area. So this is the area of a square. So it's going to be L squared. And so that's equal to 0.1 and times cosine of 33 degrees, basically. So that's the total flux. So this is this L squared is the area of a square. The geometrical structure you have here, that's a square. The sides are L, and so L squared is the area. So put in this value, 0.1 is in meters. That's the proper unit, so no conversion needed. And the 24.6 newtons per coulomb, that's in the standard and correct unit. No need to make any conversions. And just plug and chug. So let's see what we get. So you have 24.6 times 0.1 squared times cosine of 33. And let's see what pops out. So there seems to be this is a 0.2063. Okay, and then the unit, the electric field is newtons per coulomb. You're multiplying by an area which is meter squared. So it's Newton meter squared per coulomb. Okay, and does that agree with the answer in the book? Okay, good. But you see, so that's basically your homework in a nutshell. So any questions or thoughts? Okay. So I can stay and chat for as long as you want, but this kind of concludes the homework part of this whole business. So I'm going to scan these sheets, and there'll be like a PDF document of all of these sheets together. I'll post them. I'll email you the place where I'm going to post them. And then this recording also, I've been recording this, as you know. I'll go ahead and try to post it on YouTube. That can take a while. This has to be edited and rendered. The rendering takes a couple of hours for every hour. And then to upload to YouTube, because this is more than a high definition. It's ultra high definition. So it takes almost like 3 hours, 2-3 hours to upload a 1 hour video. And this was longer than an hour, okay? So it can take a while to get there, but you can replay this whole thing. And I mentioned in preparation for the quiz and future tests, I've made recorded lectures of everything taught so far in class. It was done using this format without an audience, so it sort of goes quickly. But of course, you can pause and you can play it at a slower speed on YouTube and replay and stuff like that. And plus, it has captions. So if you look through those, if any of the theory is fuzzy, look through that. And as I mentioned, try to find study partners or a study group. And if you need any help with that, let me know if you don't know anybody in class, and I can try to hook you up. Okay. So that's it as far as the formal lecture is concerned today. And on Wednesday, I assume there will not be any severe weather conditions and stuff like that. So everything should be as normal. But feel free to chat with me if you have any questions, any thoughts. It doesn't necessarily have to do with this chapter of physics even. But if not, then I'll see you on Wednesday. But
I do have a question.
Sure.
It's from all the problems. I think it was. Here, let me find it. I think it was question 16.12.
Okay, Rylan, do you have a camera on your computer?
Oh, yeah, sorry.
Okay,
I forgot to.
sure. Okay, 16 what is the number again?
16.12.
16.12. Okay, let me look this up. So this is not from the homework.
No.
Okay. For some reason, I opened that document, Physics Problems All, after I started this software, the platform. So it's not able to see it. Let me try again. Let's see. But if not, I'll just read it. Let me look here. Oh, it's there now. Physics Problems All. Okay. Here we go. Okay, 16.12 you said?
Yes.
Let me make this bigger. Okay. Ellie, are you able to see this too?
Mm-hmm.
Okay. Okay, so let's all read it. Suppose the attraction between the moon and the earth were due to Coulomb forces rather than gravitational forces. What would be the magnitude of the charge required if equal but opposite charges are resided on both earth and moon? Mass is so much, moon is so much, distance is so much. Okay. So let me just write this down. Let me write this 5.98 10 to the 24. And the moon is 7.35 10 to the 22. And the distance. And the distance is, what is it? 3.84 10 to the 8. Meters. Okay, I wrote the problem down, so I don't need this anymore. Okay. So here is the question then. You have the Earth and the Moon they're held together by gravitational forces. You have gravity keeping the moon tied to the Earth, basically. And the distance is so much, 3.84 10 to the 8 meters. They give you the masses of the Earth and the moon. So the question is, if gravity were just gone and instead you had electric forces holding those two things together, how much electric charge would you need on the Earth and the moon to keep the moon in orbit, basically? So that's the question. Okay, is the question clear, Alan? Okay, that's what they're trying to find. So when they're being held together by gravity, the force of gravity is equal to G m1 m2 over r squared. So this is Newton's law of universal gravitation. The force between two point charges or two spherical masses is equal to the masses multiplied G over r squared. In the electric case, you have Coulomb's law, which replaces this. So in the Coulomb's case, in the case of electric charges, the force electric is equal to K Q1 Q2 over r squared. So very similar looking structure for the equation. But here you have Coulomb's constant, there you have Newton's law of gravitation. So you want the same force. That's the whole point. So here they say that Fg is equal to Fe. You want it to be held together with the same orbit, not farther, not closer, also taking 28 days to go around the Earth one time. The lunar month should not change. So now and Q1 equals Q2 as far as these equations give you only the magnitude, but the further fact is that Q1 is equal to Q2, and we are concerned with magnitude. And what is that charge? That's the point. You have a minus and a plus. It doesn't matter which is which. So now go ahead and put those expressions in. So you have G me mm over r squared. This is equal to K Q squared. I'll just call this Q because they're the same. K Q squared over r squared. And this is the question. So notice that the r squared will cancel, and so therefore Q squared, Q squared will equal G me mm over K. Are you with me so far?
Yeah, so I was confused. So I divide G by K as well?
Correct. Yeah, this is what you get. When you rearrange this equation to find Q squared, you get this.
Okay.
Okay. And so therefore Q will be the square root of all of that. So Q is the square root of this whole thing. And and that's it. Now just put in the numbers. So you have square root. So you have G. So you have 6.673 10 to the minus 11.
And that too, for the constants, because I know all the constants that we talked about in class, and I know the basic ones like gravity and stuff, but I didn't know that. Well, I had to look it up, that G equals 6.67.
3 10 to the minus 11. So a constant like that will be given to you.
Okay.
It will be given to you. Now, on your public exams, I don't know how it works. Maybe are you required to remember big G and small k, or are those given?
For like the MCAT or
Yeah,
something?
yeah.
I'm not sure because the DAT doesn't require physics, so I won't be taking the
Yeah.
MCAT, but I assume it should.
Okay, so look into that. But for our quizzes and tests, these constants will be given. But
Okay.
this is from the Physics 201, so you may have forgotten. Okay, so now it's not going to fit in here. Let me start from here. There's not enough room to put all this there. So you have G, so this is 6.673, 10 to the minus 11 times the mass of the Earth. Okay, so the mass of the Earth was 5.98, 10 to the 24. Mass of the Moon was so much, 7.35, 10 to the 22, and divided by Coulomb's constant, which is 9 times 10 to the 9. And for our purposes, this will also be provided to you, Coulomb's constant. But it's good to remember it. I remember it, but you don't have to. And the square root of the whole thing. So square root of all of this, and that should be the answer actually. That's going to be the charge in coulombs. So, and you can crunch this out if you want. You can do it. But do you have an answer, Alan, for this? Can you go ahead and crunch this out? And
Yeah, the answer I got initially was 5.71 times 10 to the 22nd, but I didn't divide. Well, no, because I'm still getting that answer.
Okay.
Because I was gonna say I didn't include.
Did you take a square? Did you take a square? Ellie, could you also go ahead and crunch it if you have a calculator? Just have multiple checks. Never hurts to do accounting. Have redundancy in accounting, so to speak. Let's say both of you get the same answer.
Because whenever I try to check it, it says it should be 10 to the 13th, but for some reason I keep getting 10 to the 22.
Oh, Ellie, what are you getting? I can crunch it in here. Okay, hold on. Let's do it together. Okay. Okay. So isn't this a cool system? You see how I can bring like a previous sheet over here so quickly? I can do this with a whiteboard. And I have a pop-up calculator, so you can check and make sure I'm not entering these numbers wrong. Okay, so what was it? Okay, let's do the square root later. 6.673 minus 11 times 5.9, is that right? 5.98, 10 to the 24, 98. There's an 8 over here. Okay, 5.98. Oh, where is it? Okay, 5.98, 10 to the 24. 35, 22. And divided by 9 times 10 to the 9. So this is, let's do it in 2 steps, 3.259, 10 to the 27. So I have not done the square root yet. So here, square root. So the square root is 5.7, 10 to the 13.
Okay.
Is this the answer in the book?
Yes.
Yeah. You see how nice and clean the whole process is? So you want to follow the theory, follow all the concepts in a methodical manner, and success is basically guaranteed.
And last question.
Yeah.
Does it mean something different if the words are like circled in the all problems? Because
So-
I just noticed like some of them are
Oh
circled.
no, don't. This was like a old. It's a used book.
Okay.
So somebody did some circling, and then this was scanned. A former student scanned all these pages, and now we have a PDF of that. So sometimes it is like one of those hardbound books. It's hard to open very well. So near the edge, sometimes it's a little bit blurry. You may notice that because it's not very flat.
Okay.
So
Thank you. That was
okay.
all my questions.
Okay. So this will be. I'll scan these extra. This extra stuff we did. This will also get scanned, and I'll put this recording on here. Yeah.